Every single millisecond counts. In modern digital infrastructure, latency is the silent friction that is slowing everything down. This chart shows exactly how expensive that friction gets. Amazon tracked this metric and found that a delay of just 100 milliseconds, a tenth of a second, cost them 1% of their total sales. Google tracked a similar pattern. When their search results slowed down by just 400 milliseconds, they saw a permanent drop in total search volume. At their scale, that amounts to millions of lost queries every single day. For an enterprise, query speed is not a technical luxury. A slow database is a systemic financial bleed that directly impacts the bottom line. When you ask a database for information without optimizing it first, it defaults to what engineers call a full table scan. The system starts at the very first row and sequentially reads through the entire table, evaluating every single record to see if it matches your request. That works fine for a tiny spreadsheet, but when a table expands to hold 10 million user records, checking them one by one can take seconds or even minutes. In a live application with concurrent users, the whole system freezes. Yet when you search for a specific user on a major platform, the result appears instantly. You can't achieve that speed by just throwing more raw computing power at a full table scan. You have to restructure how the data is organized from the ground up. This diagram shows a B tree, or balanced tree. It's the mathematical structure behind database indexing. Notice how it looks like an upside-down tree, starting with a single root node at the top, branching out to internal nodes, and ending at a wide row of leaf nodes at the bottom. When a query begins, the database looks at that root node and makes a simple binary comparison. It decides whether your requested value is greater or less than the midpoint and follows the correct branch. As it cascades down through the middle layers, each decision mathematically eliminates massive portions of the remaining dataset. Within a few quick steps, it arrives at a single leaf node. This node holds the exact physical pointer to the specific row of data you requested in the main table. Instead of scanning 10 million rows one by one, the database checks perhaps 30 or 40 nodes to find the exact same answer. Indexing takes a linear marathon of brute force reading and turns it into a highly efficient logarithmic shortcut. Because applications query data in countless different ways, engineers rely on specialized variations of this index structure. A clustered index physically reorders the actual rows of data on the storage drive to match the index order. A non-clustered index, on the other hand, leaves the original data untouched. It builds a separate external map of pointers to track where everything lives. If you need to filter by multiple attributes at once, you use a composite index. But there is a strict rule. It only works if you query the data in the exact order of the columns you group together. There are also unique indexes to guarantee no duplicate records exist, and full-text indexes, designed specifically for scanning large blocks of text for keywords. Combining these varied structures gives a database architect a complete toolkit to eliminate almost any read latency. If indexes wipe out expensive latency, the logical assumption is to put one on every single column in the database, but doing that is a costly mistake. There is a strict trade-off in database physics. Indexes exponentially speed up reading data, but they actively sabotage writing data. Every time you run an insert, update, or delete operation on an index table, the system is forced to do extra work. Adding a single new row of data forces the database to pause, fracture, and mathematically reconstruct every single B-tree index attached to that table. Pile too many indexes onto a table, and it ultimately chokes on its own structural overhead, grinding to a halt during high-volume data entry. In a live transaction system or an active order management platform, this write penalty breaks the application just as surely as a slow search does. The golden rule of database architecture is strict curation. You only apply indexes to columns that you search frequently, and they must contain highly unique values. Putting an index on a column with only 2 or 3 possible options provides no meaningful speed advantage, but you still pay the full mechanical penalty every time a new record is saved. True database architecture isn't about indiscriminately applying speed boosts. It is an economic balancing act, knowing exactly what to leave unindexed.
If you found this helpful, please hit the like button and subscribe for more.